Problem 18, chapter 4, section 5. So I'm going to read it first. Then I'm going to talk through the way I would read it and what would go through my head. And I'm just going to basically talk through what goes through my head when I go to solve a problem like this. So at a county fair, adults tickets sold for $5.50, senior tickets sold for $4, and children's tickets sold for $1.50. On the opening day, the number of children's and senior tickets sold were 30 more than half the number of adult tickets sold. The number of senior citizens tickets was 5 more than 4 times the number of children's tickets. How many of each type of ticket were sold if the total receipts from the ticket sales were $14,970? Okay, that's what it says. This is how I would read it. At a country fair, adults tickets sold for some amount of money, senior tickets sold for another amount, children's tickets sold. Sounds like we have 3 things going on here. On opening day, the number of children's tickets and senior tickets were related somehow. The number of senior tickets were related somehow. And how many of each type of ticket were sold if something? Okay, how many of each type of ticket? How many of each? They're asking me. And like I said earlier, we have 3 things. And the things that they're asking me are the adult tickets, senior tickets, and children's tickets. And they are asking me how many of each type of ticket. Okay, so this is the first thing I would do right there. Puzzled this through a little bit, and I've said the thing that they're asking me, like that's the thing that I really need to identify. What are they asking me to find? We need to know the number of adult tickets, the number of children's tickets, and the number of senior tickets. That's the only thing we don't know. And that's what I need to find out. So I'm going to name these variables. This is going to be my first step. I'm going to say let A equal the number of adult tickets sold. C equals the number of children's tickets sold. And S equal the number of senior tickets sold. Okay, that's what they're asking me. I have it written down on my paper. Cool. Then they say, they give me some information. They say the adult tickets have a certain price. Okay, so what I'm going to do is this. And this is going to help you very, very much for the rest of the time that you do mathematics with any sort, especially when you go into calculus, this type of thing. I notice that so first off, this is the number of tickets. A is a number of tickets. It should be an integer. It shouldn't be like, well, first off, it shouldn't be a negative number because you can't sell negative tickets. It shouldn't be like 0.7 or anything like that, like 75.7, because you can't sell 0.7 of a ticket. And then they give me this price. And what I'm going to think about that is that's a rate. It's like it's dollars per ticket. So I'm going to go ahead and write that here with this information, but I know that what I'm about to write here has nothing to do with this number that I'm looking for. I'm trying to find the number of tickets, but I like to organize this together. And I'm going to say, okay, well, this is at, like, the rate of that ticket is $5.5 per ticket. This rate right here. Thinking of things in terms of a rate, in other words, like one quantity divided by another quantity, kind of like a rise over a run, if that sounds familiar. That's going to be really helpful to think about things in those terms. So I'm going to think about anytime I see something like a price, or back to our question that we did last time, I said we had like 3% acid, right? And so what we could think about in that case, we said that X was the number of milliliters of 3% acid. So translated into this type of thing, we could say, well, that's the number of milliliters, and the rate is at 3%. In other words, 3 parts acid per every 100 parts liquid. So it's kind of the same thing. It's still kind of like a rate, right? Only when we go to do it, we think about it as a decimal, right? We think about 0.03, but that's what that means. That is parts acid per parts liquid, or parts total, we could say. Right, so it's kind of the same thing going on. It's hard to see when you're given like 3% acid, because you think that percent just means change that number into that number. But what's really going on here is you're talking about parts acid per the total parts. In other words, it's a fraction, it's a rate, it is a slope. So that's how we want to start thinking about these things. So, and it takes some time to get used to, and you can't always identify it, but start doing this now. Okay, so, and that was my aside. Okay, so now they said that the cost of the child's ticket was 1.5. So that's at $1.5 per ticket. And the seniors, their price was $4 per ticket. Okay, so that's my information. Now I'm going to go through and say, okay, so I have 3 unknowns. That means I need 3 equations to solve it. Let's see what information they give me. They say on opening day, the number of children and senior tickets sold. And so it's so tricky. This is why I love this problem. Why I assigned it is because you think, well, where does this come into play? It tells me that the number of children's and senior citizens tickets sold was 30 more than half the number of adults tickets. And you're like, where do I put the 5.5? Where do I put the 1.5? Where do I put the 4? This is deliberately tricky because it does not come into play here. It just says that the number of tickets, here we go, the number of children's and senior tickets. So I'm just thinking, oh, well, that's children and senior tickets, that's C and S. So then the number of children's and senior tickets sold was, it says 30 more than half the number of adults tickets sold. And I think you wrote this right last night. And you might have had everything right when you actually wrote it out last night, but I really wanted to talk about it. So then you said, and I think you did this, you said, okay, half the adults tickets. So that would be A over 2. That is equal to, but it's actually 30 more than that. So we're going to go plus 30 right there. Okay. Yep, that looks good, because that says the number of children and senior tickets is 30 more than, yes, it's 30 more than half the number of adults tickets. Okay, I think I've translated that right. So we have 1 equation, 3 unknowns. That means we need 2 more equations. Let's see what else we have here. And then it says the number of senior tickets was 5 more than 4 times the number of children's tickets. Okay, so the number of senior tickets sold was, the number of senior tickets sold was, so the number of senior tickets is equal to 5 more than 4 times the number of children's tickets sold. So if I take 4 times the number of children's tickets sold, it's still not enough. I need another 5 because it says it's 5 more than that. So now I go plus 5. Yeah, that looks good. That says that the number, because again, and I love having this up here because at this point, by the time I've written this second one down, I don't remember anything that's going on. I'm like, wait, hold on. What does this mean? The number of, yeah, okay, that means the number of senior tickets sold. Yes. And it is what I would get if I took 4 times the number of children's tickets, 4 times more than the number of tickets, and then another 5. Yes, that is what that said. Nice. Okay. The two equations, 3 unknowns means we need one more equation. So I'm going to keep reading because something like, let's say that there were some, like they gave you a whole bunch of information, right? Like they might have said the total number of tickets sold was 502, in which case, like, then we'd have a choice of what we could do. What I'm getting at is like, you start writing down equations, and once you get 3, stop. Like, in this case, they give you just enough information, which is okay. So, moving on. How many of each type of ticket were sold? Yes, if the total receipts from the ticket sales were $14,970. And that, right, they're telling me that we get $14,970. And I think you set this up right both times, but I want to talk this through because reasoning this through is going to help you in chemistry and physics and mathematics, especially if you go to take calculus. And I'm pretty sure with stuff we're going to be doing later this year, this type of reasoning is going to make sense. It's like they told me that something is equal to money. The variables I have are not equal to money. What do I need to do to turn one of those guys into money? And what I'm thinking here is, oh yeah, that's right. They gave me this rate. So just kind of what's going through my head here is if I take number of tickets, in other words, one of my variables, if I took one of my variables, what would I need to do to turn that into money? Well, I'd have to convert it by multiplying, right? Because that's the question here. It's like, oh, I would have to multiply this number by this thing here. If I took one of the rates, that is dollars per ticket, then the number of tickets would cancel with tickets, and I'd be left with just money, which is what I'm looking for. So that's, sometimes they'll give you the rate the other way around, right? Like if you know it's at, if they say we sold these at 2 tickets per dollar, and you think, and you could get it in your head because you've done like 5 of these. Oh, I just take the rate and multiply by the variable. And that is going to hurt you because if they actually gave the information in this manner, we'd have to say, well, wait a second. If I multiply number of tickets by tickets per dollar, then I don't end up with that. I would need to divide in this case. If I divided this, in other words, multiply by the reciprocal, we would have $1 for every 2 tickets. Then I could see, okay, instead of just blindly multiplying, because I think that's what I'm supposed to do, I've done this kind of analysis. This is called, by the way, dimensional analysis, and you do it a lot in chemistry. You say, okay, I need dollars. I have number of tickets and some kind of rate. What do I need to do to cancel out the number of tickets and give me just dollars by itself? In our case, it is just multiply the number by the rate. But if they were tricky and gave you the rate as tickets per dollar, then you'd have to know, okay, well then I need to divide by that amount because this ain't gonna work. I would need to get number of tickets times, I would flip that fraction and get dollars per every 2 tickets cancel, and I'm left with just dollars, which is the quantity that I want. But in this case, right, I've kind of taken a couple seconds to think it through and say, yep, okay. Then the total amount of money I would get would be what I would have if I, and you could kind of reason this out without having to do this, right? You said, say that we knew they had 5 that we sold a total of 5 tickets, and we know that it was $5.5 per ticket. then we'd say, well, just multiply 5 by that, and you would have the total amount of money. And that's great because it's somewhat simple. At least this part of the problem is somewhat simple. We don't really need to go into all this stuff, but it's good to think about it like that. Okay, so moving on. I'm going to say then the total amount is what I'd get if I knew the number of tickets and I multiplied by the rate. So that gives me 5.5 times A. And then in this case, 1.5 times C. And then 4 times S. Just like that. Okay. 3 equations, 3 unknowns. And so what I'm going to do then is I'm going to go ahead and think in my head, I want to set up my matrix so that I have A's in the first column, I have C's in the second column, I have my S's in the third column, and then I have my pure numbers, my constants, in the last column. Why choose it that way? Well, because that's the alphabetical order, and that's just how I like to keep things straight. You see, I went ahead and wrote it that way here. So in this case, it's like I need to get that A over on that side. So I'm going to go ahead and subtract the A over 2. That gives me minus A over 2 plus C plus S equals 30. So I'm going to go ahead and move this guy over to give me some room. This is S equals 4C plus 5. Okay, almost there. Now I noticed this would be a really nice, in fact, it would be a nice first equation because we have that A all by himself. We don't have an A here. That A is yikes. But the thing that's messing up my life is that 2. In fact, it's a negative 2, right? So what I'm going to do is I'm just going to go ahead and multiply that entire equation across by negative 2. Kill that fraction. So I'm going to say, okay, negative 2 here, negative 2 here. The negative 2 kills that, gives me a positive A, minus 2C, minus 2S. Negative 2 times 30 is a negative 60. So that looks like a great first equation to use because I have a leading 1 right there. So I'm going to keep him like that. The second one, I need to get it in the correct order. It means I need to get the C on that side. I'm going to just subtract the 4C. So minus 4C plus S equals 5. And I can't really do anything else. I could go ahead and divide by that guy, but I'll just do all that in the matrix. That'll be fine. So that's going to be one of my equations that I use. Another thing I noticed, that would make a great second equation. Right? I mean, I could put it at the bottom. I don't want to put it at the top, but it would make a great second equation because I'm just thinking it's already missing that A. We already got a 0 for the A part. And so we would have a leading negative 4. Super easy to turn him into a leading 1 right there where we want him. So that's cool. Finally, this guy, I noticed, oh, we got decimals. I don't even want to consider decimals when I go to put this into a matrix. So I'm going to go ahead, before I even put it into my matrix, I'm going to get rid of the decimals. The way I get rid of a decimal, I want to move it 1 place to the left. I want to move this guy 1 place to the left. Have to move this guy to the right, 1 place to the right. Ditto with this guy. I need to do that. I do that by multiplying everybody through by 10. I'm not even going to write that down. I just think about that as if you were to multiply everybody by 10, it would move that decimal place 1 over, giving me 55A plus 15C plus 40S equals, I need to pick up 1 more 0 over here. So that's 149,700. There we go. Now, I have a good candidate for my first equation. I got a good candidate for my second equation. I guess we could put him third. That would be cool too. Could put him second. Could put him first if I wanted to, but I know that if I put him first, I'm going to need to get a leading 1 here, and then I'll have 15 over 55, 40 over 55, 149,700 over 55, and I don't want to have to add that into every other equation. That just sounds terrible. So I'm going to leave him like this, and we'll be able to kill him off a little bit with that guy. So putting all this together, I'm just going to go ahead and write my system, and then I will leave the rest to you to hammer this out and turn it in with the next homework. So I'm going to say, okay, my system is going to look like this. First equation I've decided is going to be this guy. I'm going ACS. This is in the order ACS. So that's going to be a 1, a -2, -2, -60. Second equation, the A is not there, so we got a 0. -4, 1, 5. Finally, 55, 15, 40. Okay, so 55, 15, 40, and 149,700. And I can kind of see I'm just anticipating what's about to happen. I got my 0 here, so I won't need to add him to here. And I can just see like, yeah, okay, I'll have to multiply this by -55, or yeah, by -55. That's going to give me a number here. That's going to be a big number, and he'll actually start either chipping away or adding up on this guy. But that sounds right. Anyway, I'm talking too much. At this point, we have a perfectly good matrix to go ahead, row reduce, and then back substitute, and we would be done. Any questions?
No questions.
Cool. Okay. So I think, yeah, I think you had this. I'm not sure if you had this one or not. I think when you sent it to me, I was just like, you know what? Let's just talk about this tomorrow, because this is tricky. It was very tricky because, and you absolutely, when you see it, like with every equation, you're like, where does the 5.5 come in? Where does the 1.5 come in, right? And that's just so tricky about this is, and it's a lot. Yeah, buddy, I know. Here, have some banana. Have some banana. I know, you really want a banana. Yeah. Okay, here, have a bite. Have a bite. Yeah, and so like, and I could tell that's what, when you first sent me your text, is like, what's going on? How do I piece this together? And you're thinking these have to show up somewhere, right?
Yeah.
It's a lot, and they do. It's just not in every equation. And it's kind of like that problem that we had last time with the acid, right? That with the acid, in one of them, it's simply x plus y equals 500, right? Just the number of milliliters plus the number of milliliters equals the total number of milliliters. And then in the second one, then we had to multiply by the rates or the concentration of acid. And so it's subtle, right? Because you're thinking these have to show up somewhere, and you think they need to show up in every equation, right? Yeah, no, that's what's so difficult about this one. That's why I signed it. So, okay, moving on to chapter 4, section 6. We are talking about consistent and dependent systems. So first off, let's get a system of equals. How about let's do one we've seen before, or something like what we've seen before. We've seen this. How about this? How about okay, let's say I gave you this system right here, and we wanted to solve it. What we would do is plug it into a matrix and do some stuff, but let's not think about it that way first. Let's think about it in the way that we first did when we first started talking about this stuff. We said, well, hold up, you gave me 2 lines, right? This line right here, I bring the y over, bring the 1 over, and put it into the canonical form. Y equals x plus 1. That's one line. I'm just going to double check. Yeah, bring the y over gives you a positive y. Take the 1 over gives you a positive 1. Yeah, that's that guy. Now this guy right here, let's see. I want to put him in canonical form. We get 2y equals 2x plus 1. I need to divide that guy through by 2 to give me that guy right there. Okay, y equals x plus half. Okay, so I have 2 lines, and immediately what goes through my head is, well, we could graph these 2 lines. I know what they look like. Right? And in fact, when I'm graphing something, I think about it in terms of a function. And so we have 2 functions, f of x and g of x. Let's see, plug in a 0 into f, you get out a 1. Plug in a 1, you get out a 2, and so on and so forth. This is a line. This is the line f. Okay, somebody wants some more banana. Take a bite. There you go. Okay. Now, the other one, the same kind of deal. Plug in a 0, you get out a 1/2. Plug in a 1, you get a 1.5. Like that. And indeed, this is a line. It goes like this. That's not a line, but you get the idea, right? Okay, so now what we did before, right? The idea was we wanted to find a place, we wanted to find an x value that made these, an x value and a y value that made these 2 equations simultaneously true. And so what we said is, well, if we think about this as functions, we could say we want to find an x value. I can use red and say we want to find an x value such that when I plug it in, the output of G is the same thing as the output of F. And now that we've graphed it, you could see that this is impossible. But let's pretend that we didn't graph this. Right? Let's pretend that we didn't graph this at all. And we're supposing that there is some input X that you could plug in that gives you the same value for F and for G. In other words, and this, I'm just mirroring what we did last time. We said, okay, we want to find the special X that makes the outputs of F and G equal to each other. And what would we do? We'd say, well, f of x, the output of f of x is x plus 1. And so we'd say, okay, there's x plus 1. Just plugging along like we did with the last time. And we said, okay, the output of G is x plus 1/2. So how about I get all my x's on one side, all my constants on another side? So how about I bring my x over here? I'm going to go, okay, I'll bring my x to this side. Okay, that gives me that. That gives me that. It's a 0 and a 0, and I get 1 equals 1/2. Well, maybe if I subtract a half to get it over to the other side, maybe life will, 1/2 equals 0. 1/2 is never equal to 0. I'm just going to go ahead and state that now, that 0 is only equal to 0, right? So what do we conclude? We'd say, well, if this is never true, that's never ever true, then this can never be true, which means that that can never be true, no matter what value of x you plug into it. Therefore, this can never be true. So there is never a time where the output of F equals the output of G. And then we're back to the picture. And yeah, that makes perfect sense, right? Parallel lines should go on forever and never touch, right? Or do they? As an aside, let's just talk about this real quick. If I drew a line, if I took a, let's say a laser, I don't know, I'm not gonna say a laser, but if I just drew a line in this direction forever, right? It just went as far as I could. And then I went, say, 10 feet this way and drew a line forever. Yeah, those would never touch, ever. But if I turned in this direction and drew a line directly in that direction, and then went and did it parallel, so that it intersected the first line that I drew perpendicularly, and drew it in that direction, those two lines would touch. Do you know why that is?
What two lines? The new pair, the new two, with the new
But
two
if-
pair lines, or
So I told you, in the first case, we're going to draw a line into the whiteboard that way. And then we're going to move 10 feet this way and draw a line that way.
Yeah.
Okay, those lines would never touch, ever.
Okay.
And now let's just take that first line that I drew, and I'm going to go perpendicular to it and draw a line in that direction. And I'm going to move some distance and stay perpendicular to it and draw a line in that direction. And I'm telling you that those two lines that I drew in that direction will touch at one point. You're like,
Wait. What?
I'll tell you why. I know this is. I'm trying to be weird because we are on the Earth, and it turns out that that way is east. And so if I drew a line to the east, it would go around. It would come all the way back around the Earth. It would come back to the original point. And then if I moved over a little bit and drew another line, it would also be going due east. And it would go all the way around the Earth, come back around, and those two lines would never touch. But then if I turned in this direction, that happens to be due north. And if I drew a line that's perpendicular to this line, and it would go due north, and it would go through the North Pole. I moved over a little bit and drew another line that was perpendicular to the first line that I drew, it would also be due north. And so yes, it would curve, but it would hit that line right there because we're on a globe. So if you're on a globe, it's possible that two parallel lines can touch, even though they're parallel, right? And it's easier to see if you think about, okay, we're in Seattle, go due north. Now go over to, say, I don't know, somewhere in China and go due north, then yeah, those are parallel lines, but they would end up touching at a point. So parallel lines can touch. This is an interesting thing. So Euclid, you know about Euclid?
That's what I did last year. Euclid geometry.
Okay. So Euclid had, I think it's called the fifth postulate, right? It's the parallel postulate, that parallel lines never touch. Well, and you can't prove it. That's why it's called a postulate, because it can't be proven from first principles that two parallel lines never touch. You have to say, well, I guess we're just going to go with this. It's a postulate. It's like an axiom. We're just going to throw it out there that two parallel lines never touch. The reason you can't prove it is because if you're on a globe, it happens to be false. Same thing. If you're on a saddle, so we're talking about a space that's shaped a certain way. And if your space is curved, if it has what we call positive curvature, like a globe, then it turns out that those parallel lines can touch. If you're on something that's curved differently, like if you imagine a saddle on a horse, right? Where it kind of does this kind of thing, right? So like your legs would go over here. Well, it turns out that in this case, parallel lines can actually get farther away from each other. It's a terrible drawing, but you can imagine, right? Like a saddle, and like you have two parallel lines, and as they start to go, they actually get farther away from each other. So this is just an aside. I just want to say it's not true that two parallel lines will never touch. If you're on a globe or on a sphere, they can touch. It depends on their direction, but they can touch each other. But we are not, in this case, we are not on a globe. We are not on a saddle. Our space that we're going to consider is a plane. It's called a Euclidean space because of Euclid. And we're going to imagine that this plane is flat and it extends everywhere it's flat. It never curves back around to become a sphere or anything like that. No surprises. We're on a plane. And in that case, if the plane never comes back around on itself, then yes, those two parallel lines that we drew at the beginning will never touch. They'll go on forever and they'll maintain the same distance between them forever. Okay, so that was an aside. Like, I just had to mention that because, yeah, I just had to. So, okay, what does that mean for us? Well, in this case, we could see from like the picture and from the fact that we got something that was contradictory. 0 is not equal to 1/2, right? We could see that there is no solution to this system. That is, system has no solution. Explicitly, there is no point xy which makes both equations simultaneously true. Simultaneously true. That was the whole point, right? That's where we started off with all of this. When we have multiple equations, we want to know, is there one value of x and one value of y that will satisfy the first and satisfy the second at the same time? In this case, there is none. And that can be seen by the fact that these are parallel lines that don't touch, right? It's impossible for them for them to both be satisfied. So okay. We call this an inconsistent system. Inconsistent, T-E-N-T. Inconsistent system. All right. But in practice, we're not going to draw lines and try to see if they touch. If you're given a system of 3 equations and 3 unknowns, you are not going to draw planes to see if they ever touch. What you're going to do is what we've been doing is plug this guy into a matrix and see what happens. And let's see what happens when we have an inconsistent matrix and we try to row reduce and back solve this guy. So what is this system written as a matrix?
1, -1, -1.
Yeah. And then?
-2, 2, 1.
Okay. Now what do I do?
Make -2, 0.
And so what do I need to do to the top equation?
1. Multiply it by 2.
By 2? I like to do it by -2, personally. Or yes.
Oh.
No, I don't. No, you're absolutely right. Yes. Multiply it by +2, Justin. So we multiply that whole thing by +2. We get a -2. And then +2 and a -1 give me a -2. Okay. Now. Okay, I'm not touching the first equation. Okay, now what do? I add that to the bottom equation. What do I get?
0, 0. -1.
-1. Now, here we go. This is the sign that you have an inconsistent system right here. What this means, let's just kind of translate this back into equations. This says that 0 times x plus 0 times y is equal to -1. In other words, it's telling me that 0 is equal to -1, which it does not. And we can see we end up with the same type of contradiction that we would get if we tried to set these guys equal to each other and find an x that makes them both work. We end up with a contradiction. Okay, so in other words, and this, by the way, is shorthand for contradiction right here. It means like you're going this way, but you can't go that way. You're contradicting each other. So this is a contradiction. When you end up with a contradiction, it means your system is inconsistent, which means there is no solution to your system. Okay, be careful. Because what if you had row reduced something and you end up with, say, a system that looks like this? Is there a contradiction there? It looks awfully similar, right? Like what I'm getting at is it's like you have zeros everywhere except for one place where it's not a zero. Same kind of thing here, zeros everywhere except for one place where it's not a zero. But if we translate this guy and say, what does that mean? Well, it means that 0 x's times 1, or I'm sorry, plus, oh, excuse me, 1 times y is equal to 0. All this tells me is that y is equal to 0. That's perfectly fine. That might be a solution. So this is not this system. This is just something I just made up, right? It's possible that y is equal to 0. Like for instance, if we had these two lines right here, if we had the line that came down like this, going through 1, I guess this would be y equals negative x plus 1. And we had the line right here at negative 1 going up with a slope of 1. This line would be, I guess, y equals x minus 1. It does turn out, and you can kind of see that 0 is the y value where they are both equal. And so if you were to do this system right here, let's just do it. Turn this into a system. We have x plus y equals positive 1. This guy is minus x plus y equals. We started off talking about an inconsistent system. And we said if you have a bunch of zeros equal to a constant that's not 0, you have a contradiction. But just because you end up with a system where something like this happens, where you have a 0, 1, and then a 0, doesn't mean that that's inconsistent. It just happens to be the case that y is equal to 0. And then I said, well, for instance, if I had two lines that intersected where the y value happened to be 0, which is the case with these two lines, they intersect here at y equals 0. If we turned them into systems of equations like this, I just took that line, turned it into standard form, took this line, turned it into standard form, and said, this right here, x plus y equals 1 is that line. Negative x plus y equals negative 1 is that line. And I said, if we tried to solve that by putting it into a matrix, we would have 1, 1, 1, negative 1, 1, negative 1, which I would then take the top row, add it to the bottom row, and get 1, 1, 1, and then 0, 1, 0. Or, oh, no, I'm sorry, I went this way. So you would get 0, 2, 0, which is the same thing as 2y equals 0, which is what that is. I said, well, or we could just keep going along, divide that guy by 2 to give us this guy right here, which just again says that 0 x's plus 1y is equal to 0. It's just telling you that y is equal to 0. So there's no contradiction there. Then I said we could just continue on to solve this system by taking negative 1 times that row, adding it to that row to get this system. The solution to my system says that x is equal to 1 and that y is equal to 0. And that's exactly what we see here. When x is equal to 1, both outputs are y equals 0. Or we could just plug this 1 into here. We get 1 plus 0 equals 1. Check on the first equation. Negative 1 plus 0 equals negative 1. Check on the second equation. So that's cool. My point in this right here is to say this is a completely different monster than this right here. Just because you have everything zeros except for one entry, that doesn't happen to be a contradiction. But when all of your zeros are on the equation part, and then you have a constant right here, that is a contradiction because of what it means. In this case, you're saying that 0 equals -1, which is not true ever. In this case, you're saying it just happens to be that y is equal to 0. So we just got to be a little careful of that. So like when you get a system and you see something like this, don't think, oh, it's inconsistent. No, it just happens to be that y is equal to 0. Does that make sense?
Yes.
Okay, cool. So, okay, man, I wish we wouldn't. All right, we got one more thing to talk about with this before you could move, before you're ready for the homework. Okay, so here's these systems. I'm going to go ahead and erase pretty much everything. All the systems we've talked about up to now was consistent. They were consistent, meaning that there was no contradiction. We all, the lines that we had, or the planes that we had, they all intersected at one point. There actually was a solution. That is, there was one point that made all of the equations true. We just saw a case of parallel lines where there is no solution. We call that an inconsistent system. There's one other kind of system we need to talk about, and that would be what would happen with this guy. Now, in the first case, we could solve this, and we would, if we were going to put this into canonical form, we would have, like we had last time, y equals x plus 1. I can bring the y over, bring the 1 over, and you get that. Now, in this case, we would have 2y equals, bring the -2 over, give me a 2x plus 2. Divide everybody by 2. And we get y equals x plus, oh, hello, that's the same line. So they're parallel lines, but they happen to be the same line, right? Like, we don't want to get it in our heads, oh, parallel lines, that means no solution. Well, unless it's the same line, in which case, now I'm just gonna go ahead and graph this. That is my F. And then if I wanted to graph my G, well, it's the same exact line, right? So if we were to ask, what is the solution to it? Well, there's infinitely many solutions to this system. In fact, anyone that satisfies the 1, so I plug in a 1, I get out a 2, is going to satisfy the other one. When x equals 1 and y equals 2, you get 1 minus 2 equals -1. Plug that same point into your second system, you get -2 times 1 plus 2 times 2 is equal to -2 plus 4 is equal to +2. And that one's true. In fact, any one along here is going to work. Any point on that line, every point on that line will be on that line. We call this a dependent system. A dependent. That is a dependent system. And it happens when you have a multiple of the same line. Multiple of the same line, plane, hyperplane. We have not talked about the geometry of the 3x3 system or the 4x4 system or the higher dimensional systems. I really wish we had time to, but we don't, and we're gonna have to leave it behind. But it's the same way 2 equations define a line, 2 unknowns define a line, 3 unknowns define a plane in space. 4 unknowns define something we call a hyperplane, and so on and so forth. So it turns out, so a dependent system is one where one of your equations is simply a multiple of the other. And you can see that. That's in fact how I calculated this. I just took this number, right, this equation right here. I multiplied it by -2, and I got this new equation, which if we wrote it in canonical form, we could see it's the exact same line. And so we have a dependent system that arises from having a multiple of the same line or object. And there are infinitely many solutions. Okay. So what would that look like if I used my matrix? Okay, so that's what I'm going to do now. I'm going to say, because I'm not going to, especially in a 3x3 or a 4x4 case, I'm not going to solve for some variable and set them equal to each other or see that they give me the same thing. What's this going to look like if I just plugged it into a system or into a matrix? This system in a matrix would be 1, -1, -1, -2, 2, and 2. And right away, you can see what's going to happen, right? In order to turn that into a 0, I need a +2 right there. So I'm going to multiply everybody through by +2, just like we did last time. 2, -2, -2. Add the top to the bottom and let's see what we get. The top row has not changed. The bottom row now becomes 2 and -2 make 0, -2 and 2 make 0, -2 and 2 make 0. We have an entire row of zeros. And that's how you'll know. If you get an entire row of zeros, well, the only way you could get an entire row of zeros is if one of the equations that you had was simply a multiple of another equation. If one equation is a multiple of the other, then they're the same thing, which means that there are infinitely many solutions to that guy. You see how that works, right? I've basically stated the same thing a few different ways, but that's going to be the key right there. That's how you'll notice it. And this can happen at any time, right? Like it might, especially like if you have a 3x3 system or a 4x4 system, if at any time as you're solving, you get an entire row of zeros, you could stop and say, this is a dependent system. There are infinitely many solutions. Done. I am not going to worry. We're not going to worry. We could talk more about, well, what type of solutions would they be? But we're not going to do that in this class. So if you take linear algebra, you'll be talking about that all day and night. But right now, when you go to do these, when you get a dependent system, it's as soon as you get an entire row of zeros, you stop and say, the system's dependent, infinitely many solutions. Okay. So, any questions? First type of system is consistent. It has exactly one solution. One and only one solution. And it's what happens when you row reduce your matrix and you get this nice row of ones right there. When you get, your nice diagonal of ones right there, then as soon as you get that, you can always back solve and clear out that part right there. One solution, we call this a consistent system. Okay. Another case is you doing your system, you're going along, and then all of a sudden you end up with an entire row of zeros. And you have some other stuff here. Doesn't matter. Doesn't matter where it occurs, when it occurs. As soon as you have an entire row of of zeros, you have what's called a dependent system. It's also consistent technically, but we're not going to worry about that. that. It's a type of consistent system. You don't have any contradictions. There's nothing saying, like with those two lines, there's no contradictions with those two lines that happen to be the same line. So it's not inconsistent, but it's a special type of consistent system that we say is dependent. And there are infinitely many solutions. The final picture is you're going along, you're solving your stuff, and at any point along the way, you end up with an entire row of zeros except for the last thing. This last thing right here on the far right is not zero. We'll just call it A. It's some number that's not zero. Doesn't matter when it occurs, doesn't matter where it occurs. It could be the top row, it could be the bottom row, it could be one of the middle rows. As soon as you have a bunch of zeros here and then a constant over there, well, what does that mean? It means that 0 equals something that's not 0. That's impossible. That's inconsistent. That is a contradiction. Inconsistent system. That means there is no solution. Okay. Big difference, right? Like it's possible that one of these numbers might be a 0. Don't think, oh, everything's 0 in this row except for one number, therefore it's inconsistent. No. That only happens when everything on the left-hand side of the equation is equal to 0. And then you have something on the right-hand side that is not equal to 0. It's possible that one of your variables just happens to equal 0. That's consistent, that's fine, one solution. An entire row of zeros, that means at least one of the things is a multiple of another one of the things, which means that it's the same thing. And therefore, there are infinitely many solutions. It's what we call a dependent system. Finally, you have a direct contradiction right here. You have 0 equals to something that's not 0. That's inconsistent. No solution is possible. So for your homework tonight, so it's chapter 4, section 6. Section 6? Yeah, that's 6. Okay. Numbers 1 through 23 odd. And then we're going to do 28 and 29. Okay, here's the special instructions. For this first block, 1 through 23 odd, what I want you to do is for every single system, write it as a matrix and start row reducing. If you run into this scenario, stop. Call it a dependent system and tell me that there are infinitely many solutions. Like, I want to see this. I want to see that right there. And like, you'll put a box around that and say, that right there, that is true. If you end up with a bunch of zeros over here and then something over there, stop. Say no solution. Inconsistent system. Otherwise, keep going until you get to here. Right? Until you have nothing but the main diagonal of 1s, and then write it out like x equals a, y equals b, z equals c, and so forth, and tell me that. So in every case, you are just to solve it using matrices, and if one of these things happens, stop and tell me that it's infinitely many solutions dependent system or no solution inconsistent system. With 28 and 29, those are challenge problems. You could use any method you want to do them, but the question says, determine the constant such that each system is dependent. Dependent system means that one row is a multiple of another row. That's a pretty big hint right there. One row is a multiple of another row. So You could also, so that's one way of going about 28 and 29. Another way of going about 28 and 29 is to put it into a matrix and then say, well, wait, a dependent system would have to have an entire row of zeros. And once you've done some stuff, you could say, how could I turn that into an entire row of zeros? Once you've reduced everything and got it down like this, then you could say, well, I could turn that, but ultimately they're the same thing. So you could think about it as, how could I turn one equation into a multiple of another? Or you could go along and say, how could I get an entire row of zeros out of this mess that I have right here?